One of the most important things in construction is determining that you have the proper compaction on your soil. You need to know what the maximum amount of compaction a soil can have to be able to determine where you're at with your compaction. So we have to determine the maximum dry density for these soils. And we're going to take our soil and we're going to process it down in certain cases to a -4 material. There's two different methods to this. Basically, you have your standard method, which is your standard effort, and it is a 5.5 pound Proctor hammer, and we're going to be dropping this hammer. It weighs 5.5 pounds. It's going to drop 12 inches. We've got another one that is considered your modified. So we got standard, we got modified. Our modified is going to weigh 10 pounds, and we're going to drop it from 18 inches, so it weighs more. It's dropping from a higher elevation, and so depending on your specification, you're going to do the standard or you're going to do the modified. You're going to need a lot more effort to be able to get 100% of this modified or a 95% of this modified than it would be if you used a 5.5 pound hammer dropping it 12 inches. Much more effort on this one. For today, we're going to go ahead, we're going to be doing the standard 5.5 pound Proctor. We'll take our material and we're going to moisture condition it to be 2 percentage points in between each one of these specimens that we're going to do. We're going to gradually increase the moisture of our material. That's going to allow it to compact. It's going to allow it to compact a little easier as it gets wetter and wetter, to the point to where it's too wet and it's starting to pump and you're getting displacement. So here we have our prep sample. It's ready to go. There is a moisture conditioning time for different types of soils. The clayier or the siltier that a material is, the longer it needs to rest with the moisture in it to make sure that it comes to a homogeneous point and that all the particles in it are conditioned with that water. We have our Proctor mold that we have a known volume of. The volume that we're going to fill is this right here. And when we fill that, we'll be able to determine a wet density. And then to determine the moisture content and the dry density, we're going to put that material in the sample at the moisture content with which we pounded it. So we'll do this in 3 equal lifts. We're going to do 25 blows for each lift. So there is an amount of technique to this. I'm trying to catch this before it double bounces. That'll affect your results. If I didn't catch it, it bounces off of it, and you can see that it'll give it additional compactive effort. So I have to catch it to prevent that additional compactive effort and keep it a true result. So we've kind of messed with this one a little bit, but we'll continue on just to show you the method. We'll fill in our second lift. We're going to pound that 25 times as well. Onto our third lift. We'll bring it up to the neck. We're going to go ahead and strike off the excess material that's inside this neck, and we're going to just be measuring or weighing the material that's in this volume right here. We're going to go ahead and fill in any voids that were left as a result of our cutting off that top or replacing the material. We're not adding to it, we're just replacing some of the holes that we've created. Whew. We clean that off, and we're going to get a weight of our mold and our soil. We'll be able to subtract the weight of the mold from the soil, and we'll just have the weight of the soil inside the mold, and we'll be able to mathematically determine what the wet density on that material is, and ultimately the dry density. We'll take a moisture content on it. We'll take our sample from the center of this. We'll record our weight, and then we're going to place that in the oven. We're going to be able to identify what moisture percentage that we condition this at. We'll put a tag on it, and we're going to place it in the oven to dry back. So we've pounded it at its driest point. Now we're going to go ahead and we're going to increase moisture. I did not add moisture to this one on purpose. We're going to go ahead and do that now and show you that process. We got 2195.8 grams. Our first sample was moisture conditioned to 2% above what it was originally. This one's going to be at 4%, so we'll add 4% moisture to this by multiplying 0.04. If the decimal will work, 0.04. So 4% of 2,195.8 is 87.8 grams. So I'm going to go ahead and add 87.8 grams of water to this, and I know that that's 2% of its original moisture or 4% more than its original moisture content, which is going to be 2% more than what we previously did. We're at 88.1. Our goal is to be approximately 2% from our previous moisture. This will get us about 2% of that. We're going to go ahead and mix that in. Again, we want to moisture condition this. The moisture in this material is going to facilitate its ability to compact. You cannot in your hand compact dry sand or dry soil that you pick up off the ground. It's dusty. It's just not going to compact when you squish it in your hands. But if you're to add a little bit of water, it'll compact a little bit easier. You add a little bit more water and it's going to compact easier again. Eventually to the point to where it's gushing, kind of gushy in your hand, that means that you've exceeded the optimum moisture content. That optimum moisture content is the point at which the material is the most compactable. We've added our 4% to this point. We'll go ahead and we'll run that as we had our previous point. All right, we've got our 3 lifts in here. Go ahead and strike off the top of it. We've got better moisture. You can see it's a deeper, darker, richer color. We're going to go ahead and get a weight. This weight should be significantly higher than our previous weight because the moisture has facilitated further compaction. We're able to fit more material into this mold. So we're going to see our graph rise on our dry density. We'll get a moisture on it, determine our moisture point, so we'll end up being able to graph it based on its dry density and its moisture content. We'll get our moisture pan, zero that out. We need to have a minimum of 300 grams dry for our moisture content. We'll break it down a little bit to aid in the drying of the material. We'll record that weight, and then we're going to give it a tag. There's our 4% moisture added to this one, so that'll have our 4% tag on it. We'll put that in the oven to dry back with its other point. Now we're getting into some wetter materials. This one should be a little bit over optimum. Once it gets over optimum, you're going to see that instead of having a nice, hard, firm, flat surface, as some of these were when they came out, it's going to start pumping with my hammer. Each drop of my hammer, it will displace on each side of it because you've gotten so much moisture in there that it's lubricated to the point to where, and you'll see this out in the field as some trucks will drive over conditioned material, you'll see the pump in it as that tire rolls over the top of it. So this has been conditioned to 6%. We're trying to do 2 points on our dry side. We just did our 2 dry side points, and now we're going to go on to our wetter side that you'll see displayed in a graph. So for this point, the process is the same on all 4 of the points. This one's just a little bit wetter. It's going to be over optimum, I believe, on this one. A good technician, a skilled technician, is going to be able to make that determination by feeling it with their hand. I can feel that this is over optimum. We will see some of that displacement in our mold. We want to make sure that our equipment's clean, that we don't have any material adhering to it, because that can change the impact and the force that's coming down on this 12-inch blow. And we'll go into our 3rd lift into the collar. Third lift, 25 blows. Should have 3 equally compacted lifts at the end. So with this being over optimum, it may go up a little bit on the weight and it may go down on this wet density weight. The 4th lift will definitely go down, but sometimes you're rounding the top of that curve. Moisture is going to be on our x-axis, and then we're going to have density on our y-axis. So as we get wetter, we're going to get heavier, and so it's going to be a parabolic curve. The wetter it gets, the heavier it gets, until you get to a point to where the moisture, the water starts offsetting the weight of the soil, and then you're going to see that that weight is going to go up, and then it's going to get too wet, and then your weight's going to go down. At that point where it starts to go down, that's the maximum dry density that you can have for soil at the optimum moisture content, that where it's facilitated compaction the most. We'll strike this one off. Fill in any voids. Make sure we're all cleaned off, nothing adhering to the bottom. And we'll get our weight on that. Our previous weight was 61, I believe it was a 61.88 approximately. Now we're at 61.90. We only increased by a couple grams, so that means that we've rounded over the top of it. It weighs the same based on its weight. They're both going to weigh the same amount, but one is over optimum. So we've rounded the parabolic curve over the top. Again, we're going to get our moisture content on it. This is one of the 2 wetter points that we're doing. We'll record our weight on that. We'll give it a tag to make sure we can identify it once it's come out of the oven. Just a note, a personal note, dirt, calling it dirt is kind of a bad thing in the laboratory. It's not dirt until it hits the laboratory floor. Until then, it's soil. This is one of the most important tests, I would say, for a contractor to have an understanding of. You're going to have a lot of yellow iron on grade that's going to be trying to accomplish compaction. You've got a grade level to hit, you have an elevation to hit, but you have to hit your compactive efforts that are prescribed by your specifications or your geo reports. So knowing how the maximum dry density or 100% is derived, this is that test. This tells us what 100% is in comparison to whatever your nuclear gauge or your sand cone is reading, and your technician is telling you you got a 95%, 96% you pass, or you got a 92%, you got a 93% you fail. You're very low on moisture. This is where you're very low or you're very high on moisture. This is the test that determines where your optimum moisture content is, which is the break point, the zero. If you're over optimum, it's wet, you may have pumping. If it's under optimum, you're just not going to be able to get that consolidation in the soil that you need to reach your percent compaction. All right, here we have our wettest prepared point. I could feel the plasticity has been activated in this one. We're above the plastic limit, so I can feel that it's grabbing and it's sticking together very well. So we're over that plastic limit line. I can feel it's kind of gushy in my hands, and I know that we're over optimum. Out in the field, you would get heaving, shoving, pumping, and you'd see that visually. So this is our farthest point over on the graph. We're going to be on the other side, on the wet side of that graph. Oftentimes with these materials that have a lot of clay in them, you're going to have a really low density on your maximum density. They're going to require you to place your material in an over optimum condition so that it's kind of pre-swelled. That plasticity is going to have a high swell content, it's going to have a high PI content, and you're going to be more than likely required to have a moisture condition over optimum on this so that it's pre-expanded. If you don't have it over that optimum, it's basically, and you have it compacted, so if you have it under optimum and it's very compacted, you basically have compressed a sponge. Once that water hits it, you're going to get your swell. So we'll also determine in this test that optimum moisture content that you're going to need to exceed out in the field. I am observing this material to be pumping and shoving every time that hammer hits that soil surface. It's shoving the other side up upward because we've got so much moisture basically having lubricated the particles. All right, this is our final point. It was also our wettest point. You should be able to see in this the displacement of each blow. It's pushed the soil down and lifted it on the other sides of that weight in the hammer. You can see it's even traveled up the sides a little bit on us. We're going to strike this off. This weight, the weight that we find on this one should be lower than the previous one. The previous one was 6190. Water's less dense than soil. So the more of a less dense thing if you put something that's less dense and something dense, eventually that lower density is going to offset the higher density. So I do expect this to go down because there's so much water in it, it's going to record a lower weight. All right, so we were at 6190 on the previous one. This one's going to be lower, 6157. We've pretty much fallen onto that other side of the curve, and we've dropped our density because we have so much moisture influencing that. We're going to record this, and we're going to take another moisture content on it. We're going to record that weight. I'm going to give it a tag. Throw it in the oven with its buddies. We're going to let those dry to constant weight. Once we've determined that it's no longer going to lose any weight after a certain amount of time, then we'll take that out, let it cool. We'll get the percent moisture based on its original wet weight versus its dry weight. The moisture that's evaporated is our lost weight. We know that that's going to be the lost moisture in comparison and calculated with our dry weight. We'll be able to get a percent moisture for each one of those points. And that'll help us determine our curve.